So this is the last lecture for a little while. Now I want to go over a couple of things on the quiz. Most of them were pretty good, but there were some iffies. Let me grab the key real quick here. Now on the first problem, because I did get some answers like this, okay. The first term here is going to be 27 times -4/3, which is -36. And I have a constant ratio of -4/3. So of course, the infinite sum is simply -36 over 1 minus -4/3, which I believe ends up being -108 over 7. So what's wrong with this? Because I actually got this answer several times. Can anybody tell me what's wrong with this?
The R value is not between -1 and 1, so it diverges.
This, by the way, this is a geometric series, and that is the formula for finding the infinite sum, except that the R is out of the range of good R values. So it really should say something like the absolute value of R is greater than 1, therefore, what? The geometric series, I'm going to put the GS diverges. In fact, what kind of divergence does this one have? Does it diverge to infinity? This is the one that goes like this, bouncing forever. No, this is the ugliest of all. This is the diverges without limit. I don't need you to say that, but you need to know that. This one bounces and oscillates all over the place. This is an error because we're applying a formula that is true, but only when this is less than 1. Okay, so it's very important. So if you're saying this, some of the answers I got was this diverges. Okay, that's nice. As an absolute, it's not possible to ever come to the conclusion of divergence without a reason. You can't get it diverges without a reason, and to converge means you've actually proved that. You can't just say, I just have this feeling this one diverges. It feels divergent. I don't know what that feels like, but no, this is a divergent geometric series. And by the way, you can't make an argument about R unless it's geometric. So you probably want to mention it's a geometric series where the absolute value of R is greater than 1. If you said this is less than -1, that's fine. That's the same thing. Okay, but there's got to be a reason why it diverges. You don't just say it diverges. Now, the second one, most of you set it up correctly, didn't realize there was an extra term. That was fairly minor. They kind of left out a term. On 3, 4, and 5, though, these are one puzzled me. I made these all, tried to make them all simple. I said, they all diverge. Give me a reason. The majority of the answers are, for 3, 4, and 5, they diverge. And by the way, several people actually told me what they converged to, which is not a good answer since the question starts with, they diverge, tell me why. And all I got was they diverge, or in some cases they converge. No, it was all about why they diverged. So the first one, I was hoping you just noticed, I have a multiple of a harmonic series. That's it. It's a multiple, it's a harmonic series. It's just times -4. The second and third ones, those look like maybe something's going on there. Well, in the number 4, if you take the limit of the nth term, it is not 0. So you fail the nth term test. On the 5th one, the limit of the cosine of n does not exist. So I also failed the nth term test. Remember, the nth term test is the limit has to be 0 and the terms have to be getting smaller. Okay, you don't have to show both of those things fail. You only have to show one of them fails. Usually it's the limit. So in both 4 and 5, the limit isn't 0. So they failed the nth term test. Again, by the way, there is no such thing as a specific test for divergence. Every test you could possibly perform on a series. We learned 3 last day: integral test, direct comparison, and limit comparison. Every test on a series is a test for divergence. There is no the test for divergence. That term does not exist mathematically in any context, in any textbook. So the test that we were using on these is called the nth term test. That's a test that precedes the series. That's a test where you're only looking at the individual terms. So I did get some people saying it fails by the test for divergence on all 3 questions. Well, all tests are a test of divergence. That means you didn't actually say anything. It diverges because I test for divergence and it passed the test for divergence and it failed divergence. No, you're just, yeah, you sound like you're trying to be a lawyer or something. No, you got to be very, very specific as to why. We learned 3 tests last day where the tests were on the series themselves. We're going to learn 2 more today that are very similar in nature. The first one is the most important of all tests because it's the one that is used by far the most often. And the way you're going to know it is because the next one, which is called the ratio test, primarily is for 2 types of tests. Or for 2 types of series, excuse me, for factorials and exponential functions. I'll just call it exponentials. Things like e to the n, 2 to the n, 10 to the n, things of that nature, and factorials. Now, factorials are something we're going to get really good at and we use all the time. But up until now, unless you've had statistics, you really haven't done a whole lot with factorials and combinations and things. You've seen them before, just a little bit here and there. So I want to do a quick review of what a factorial is, okay? Because I need to make sure everybody's on the same page. So when I write that, of course, I'm saying n. Well, no, that's n factorial. Sorry, I had to throw that in there. N factorial. So the first thing is n has to be an element of z plus, which is the same as saying or, n is an element of the natural numbers. Those are called the counting numbers, 1, 2, 3, 4, 5. So z plus is the positive integers, which is the same as the natural numbers. If that's the case, then this is n times n minus 1 times n minus 2 down to 3 times 2 times 1. So if I had 5 factorial, that's 5 times 4 times 3 times 2 times 1. If I had 1 factorial, that's just 1. Okay. So first of all, it has to be a positive integer to get this definition of successive decreasing. Now, it turns out when you get to differential equations, Math 255, you're going to learn something called the gamma function. You don't need to know what that is today. But the gamma function is the mathematical derivation of things that involve factorials. Factorials are a special case of the gamma function. The gamma function, I can have real number input. Factorials are only positive integer input. And it turns out in the gamma function, you can actually calculate 0 factorial. 0 factorial is calculated to be 1. That's the exception to the rule of factorials. Most people will just say, oh, 0 factorial is defined to be 1. Well, that's what we say before differential equations. Then you learn it's not a definition. It's an actual calculated value. That'd be like saying 1/2 plus 1/2 is defined to be 1. No, 1/2 plus 1/2 calculates out to the number 1. So this one here does come up, and that is 1. But the reason I don't put a 0 at the end, because then all my factorials would always equal 0, because I'd be multiplying by 0. So that's why this definition is only for positive integers, and then we throw this one in. So one of the things about factorials that helps us is if I have to reduce a factorial. So the following is true. If I said 10 factorial, that is 10 times 9 factorial. And that is 10 times 9 times 8 factorial. I can always do things like this because that's 8, 7, 6, 5, 4, 3, 2, 1. And now I'm back to here. And the reason it's important to understand these is because calculators are extremely limited when it comes to being able to calculate factorials. Most of you, if you have just a simple scientific calculator, you can only go up to 69 factorial. That's it. I have a TI-89 titanium, very, very powerful. I can go up to 449 factorial. And that's it. The supercomputer UCSD, I've heard, can go up to like 999 factorial. But wait, but integers go to infinity, and the limits of human technology is small numbers. Yeah, because factorials grow so large, so fast. So we have to understand something about them in this nature. So with this, okay, one of the things we do with factorials is the ability to calculate them, whether it be variables involved or numbers. I taught the GRE math portion at San Diego State for a few years, and I stopped a couple years ago. I just got a little too busy. The GRE is the graduate record examination. It's like the SATs for grad school. So if you wanted to go to grad school, you have to take a version of like an SAT. It's called the GRE, and it's a math test and an English test. And then typically you also take a subject specific test. So when I was in school, I had to take the general math and English, and then a separate test that was just math. You know, if you're a STEM major, you're probably going to take a separate test, a higher level for just that subject. So I taught the math portion of this. It's a preparatory course. And it would be, the course was 4 weekends, 4 consecutive Saturdays. 2 of the weeks would be math, 2 of them English. And it might be the first and third, the second and fourth, the third and fourth. It varied. And it would be all day Saturday. So I'd have 2 sessions and I would review algebra, statistics, and geometry. That's all that covered. No calculus. And the algebra, most people were fine. The statistics, I could show them enough, and the geometry required probably the most review. But the statistics, mean, median, mode, all that kind of stuff, but there were a lot of calculations. You say, well, what's the big deal? Well, there's no calculator. Well, okay, there was a little calculator on your screen that had the numbers 0 through 10 and had a plus sign and a multiplication sign. That's it. No roots, no exponents, no functions. Just so you could add and multiply small numbers, and that was pretty much it. And so there'd be questions on the GRE, you know, like this. The question might be, you know, 12 factorial over 10 factorial. And I'm supposed to multiply 12, 11, 10, 9. Seriously? Well, no. So I would show people how to be clever. So that's what you do when you can't calculate. You have to manipulate, and you have to understand how that works. Well, your calculator works much the same way. When you ask it to do calculations with really large factorials like that, it'll cancel for you. So we have to understand the rules of factorials and how they work. So with that said, what if I wanted to find out, I have 2n factorial. Now, if I wanted to expand this, what would this look like? Well, it would be 2n times 2n minus 1 times 2n minus 2, all the way down the line. Question. You can answer this. Are these the same thing? Anybody want to try that? Yes or no? Just holler out, but I'm going to make you support your answer. You think it's true or false? Yes or no?
True.
2n quantity factorial.
False.
Why? You're right, but why?
Because I got a good feeling about it. That's it.
It made you all warm and fuzzy inside. Okay, let's just pick a number for n. N is 5. All right, so the first one is 2 times 5 factorial, and the second one is 2 times 5 factorial. Well, this is 10 factorial. 10 factorial is over 3 million. This is 2 times 5 factorial. 5 factorial is 120. These are not even similar. You can't factor a coefficient out. So this means I took the number 2n and now I'm decreasing it by 1. Here's I'm taking the number n, I'm decreasing it by 1, and when I'm all done, I'm going to multiply my result by 2. That's not the same thing, but that is an extremely common error that people will make, is they will factor a number out. You can't do that. You won't get the same thing. These are not equal. Those parentheses are critical in that sense. So what the ratio test is, quite simply, if I have a series and the argument of the series is acting like it's a geometric series. It might not be a geometric series, but it's acting like a geometric series. In other words, it's asymptotic to a geometric series. Well, what makes a geometric series converge? Let's remind ourselves. So if I have something like this, n equal 1 to infinity, a1 r to the n minus 1. That's sort of the general form. Well, the a1 is not important. In fact, I'm going to move the a1 completely out. Okay? It's all about the r, isn't it? Remember, what makes a geometric series is consecutive terms have a ratio of r forever and ever and ever. It's the same r. Well, what if I had a series where the consecutive terms don't necessarily have a ratio of r, but that ratio is approaching r, like as in a limit? That means it's acting like a geometric series. Then if I have a series of the following form, let me throw a what if. What if an plus 1 over an is close to a constant. What do you mean close? We'll talk about close to a constant, meaning if I took a limit, I would get a constant. Then it would mean this is acting geometric in nature. And all I would have to do is make sure that constant was between -1 and 1. Oh. So let's write this out formally. Okay. Again, you have to recognize that you first of all, you believe that's the case. So I have the following series. Okay. If the limit as n goes to infinity, okay, mute yourself, please. And we put it, by the way, it's always an absolute value, always an absolute value. Because remember, for the geometric series, the r is an absolute value, has to be less than 1. If this is less than 1, if the ratio of consecutive terms, when I take that limit, is less than 1, by the way, it could be 0, could be 1/2, could be 0.99999. But if that ratio is less than 1, then this converges by what we call the ratio test. Now, none of the things we looked at last day, not one of them would this test apply. No, I said this test is going to apply when you have exponential functions and when you have factorials. That's it. And we'll see why. And I'm going to give you a bazillion examples today. So let's start with something simple. I have something that looks like this. N equal 1 to n, let's say of n squared over 10 to the n. Okay. Now, if I had the series is this geometric? This guy right here. Is that geometric? Anybody?
Yes.
And what is the R? You're right. What's the R?
1/10.
1/10. Yeah. How about if I look at it like, if I rewrote it like that, would that be more obvious? Oh yeah, duh. R to the nth power. This is geometric. Most of us would write this. This is considered more simple than this, although this is probably more useful because the R is a little more obvious if I write it in that form. This isn't that, is it? I got that n squared on top. But I'm going to show you that this guy here thinks he's geometric. So what do you mean? How could I get that n on top? But if n is a really large number, n is 10. 10 is not large. My top would be 100, but my bottom would be 10 to the 10th. 100 is kind of insignificant. If n was 1,000, my top is 1,000 squared. That's 1,000,000. My bottom is 10 to the 1,000th. That's a 1 with 1,000 zeros. The n on top is going to be absolutely insignificant in a really, really, really short period of time. So the way we attack this, and it's always the same setup, okay? I'm going to take the limit as n goes to infinity. Now, first thing I'm going to do, it's a quotient. It's the n plus first term over the nth term. Well, this is the nth term. The n plus first term means I'm going to replace n with n plus 1. And then the whole thing is in absolute value. Always in absolute value because that quantity can be negative. There's nothing wrong with that. Now, that looks kind of ominous. We'll obviously do a little flipping, which means that a lot of you recognize in the first step, you may have been able to just flip it anyway. That's okay. So n plus 1 squared times 10 to the n over n squared times 10 to the n plus 1. Does anything cancel? Well, those do. Those don't. So I can definitely cancel the 10s, and that would leave me a 1/10. I'm going to put that out in front. Now, at this point, I can drop the absolute value because this is a strictly positive quantity. N is approaching infinity. There's nothing negative. Okay, you can leave the absolute value in there, or you can drop it at this point. Now, look at that quantity right there. Can you evaluate that limit right there? It's a second degree polynomial over a second degree polynomial. and the lead coefficients are 1. So what is this limit right here? Anybody?
1.
1. Yeah, that was sweet. That limit is 1. Because they're the same degree, lead coefficients are 1. Life is good. So what's my answer? 1/10 times 1. My answer is 1/10. And 1/10, by the way, smaller than 1. 1 is the line in the sand in this case. 1 wasn't important last day. 1 is important today. Because a geometric series, 1 is the line in the sand, right? If the absolute value of R is less than 1, it converges. If it's greater than or equal to 1, it diverges. This is less than 1. That means, quite simply, that this thing here acts like the geometric series with an R of 1/10. Although this is not geometric, it's acting like it. Because the further and further and further, here's another way of thinking about it. This is the ratio of consecutive terms forever. So when n is getting really large, consecutive terms, for all practical purposes, this number is so close to 1 when n is large. See, if I have 1,000,001 squared over 1,000,000 squared, that's 1.00000. As n is getting bigger and bigger and bigger, this limit is getting closer and closer to 1. My ratio of consecutive terms is getting closer to 1/10 forevermore. It becomes indistinguishable after a little while. So cool. So we figured out a way to test this series by treating it as if it were geometric in nature. That's what the ratio test is. Okay, let's do another one. All right. I've got the sum from n equal 1 to infinity of 1,000 to the nth power over n factorial. Now, I want you to notice something. This one here is going to fool you. So if I said, let's write out just the first few terms, I want to see how this is behaving. So when n is 1, this would be 1,000 over 1 factorial. That's 1,000. Plus 1,000 squared over 2 factorial. So that'd be 500,000. And then I'd have 1,000 cubed over 3 factorial. 1,000 cubed is 1 billion. So that'd be 1 billion over 6. And then I'd have 1,000 to the 4th over 4 factorial. That's 1 trillion over 24. Is it pretty obvious that these terms are getting really, really, really big? You know, if I go out 100, I'm going to have 1,000 to the 100th power over 100 factorial. That's bigger than any calculator could. Yeah, these terms are getting astronomically large, unbelievably fast. So obviously this series is going to diverge to infinity. I think that's so obvious. Or is it? I've mentioned before, convergence or divergence of a series has nothing to do with what's happening at the beginning and only has to do with what's happening at that end. So let's do the ratio test on this one. So when I take my limit as n goes to infinity, let's start with the n plus first term. That's 1,000 to the n plus 1 over n plus 1, the quantity factorial. Now, I'm going to divide it by this term. Would it be legal then to multiply it by the reciprocal? Yeah, I think all of you realize after a very short time, you know what? I can always do this because if I divide it, then I'm going to have to do this on the next step. Do I get any canceling? Actually, I do, and I will get canceling of the factorials. But I first have to rewrite this one. If I said 11 factorial, that's 11 times 10 factorial. If I said 57 factorial, that's 57 times 56 factorial. So n plus 1 factorial is n plus 1 times n factorial. 1,000 to the n plus first power is 1,000 times 1,000 to the nth power. Now I'm doing that to make it obvious. Those will cancel. Those will cancel. And what am I left with? I'm left with the limit as n goes to infinity. On the top, it looks like I have 1,000. On the bottom, it looks like I have an n plus 1. 1,000 over n plus 1 is n plus 1 grows, or as n grows without bound. What's that limit going to be? 0, which, by the way, is less than 1. Therefore, this series converges. What? But those terms are getting astronomical. Yes, they are. They are getting astronomical. They're getting crazy big. But you know what's crazy about that? What is the 1,000th term? If I did the sum, the 1,000th term, or I probably should just say it this way. What is a 1,000? Well, that's going to be 1,000 to the 1,000th power over 1,000 factorial. This number is way bigger. This is 1,000, 999, 998, 997, all the way down to 1. This is 1,000, 1,000, 1,000, 1,000, 1,000. They both have 1,000 terms. The top is way bigger than the bottom. By the way, what's a 1,001? Well, won't that be 1,000 to the 1,001st over 1,001 factorial? Well, what's the big deal? Well, let me rewrite that like this. That's 1,000 times 1,000 to the 1,000th. My denominator is 1,001 times 1,000 factorial. This number is astronomically large. There is no question about that. See that number? It's right here. And I just multiplied it by 1,000 over 1,001. That means that this number is slightly less than this number. And a 1,002 is slightly less than that. Meaning from this point on, every succeeding number is a little bit less. And in fact, it's going to be a lot less in a very short amount of time. Because by the time I get out to the millionth term or the bazillionth term, this is the ratio. And that ratio is getting smaller and smaller and eventually approaching 0. Oh my gosh. So although these numbers went crazy wild, they came all the way back down. You know, it seems confounding. It seems like this should have diverged. Oh, this is going to be an astronomically large sum, but it will still be a finite sum. Because although my terms got astronomically large, they came right back down and got infinitesimally small, actually, you know, not that far away. So it doesn't matter what's happening close, it matters what's happening down the road. This series, therefore, converges by the ratio test. That's my conclusion. Whoa. Like I said, you didn't see that one coming. All right, let's try another one. So now let's say I've got the sum n equal 1 to infinity of 2 to the n over n to the 10th power. So again, if I start writing the terms down, let's see, that'll be 2 to the 1st over 1 plus 2 to the 2nd over 2 to the 10th plus 2 to the 3rd over 3 to the 10th plus 2 to the 4th over 4 to the 10th, right? If I keep doing this, it's pretty obvious. These terms are getting really small. Okay, that's 2. This is 1 over 32. This is much smaller. This is much smaller. This is much smaller. I mean, by the time I get to 2 to the 10th over 10 to the 10th, that's 1,024 over 10 billion, which is on the order of 1 over 10 million. So these terms are obviously getting really small, really fast. This one's obviously going to converge because they're getting so small so fast. Or will it? You don't think I pulled a fast one on you again, do you? Oh, yes, I did. We're going to use the ratio test. So when I take the limit as n goes to infinity, the n plus first term over the nth term, so I'm going to multiply it by the reciprocal because I'm lazy. Well, a lot of 2's will cancel, and I'll get the limit as n goes to infinity. I'll have a 2 n to the 10th, and on the bottom I'll have an n plus 1 to the 10th. Now look at that for a moment. Both numerator and denominator are 10th degree. They are both the same degree. So I can simply look at the lead coefficients. Yes, you can use L'Hopital's rule, but you have to use it 10 times. So I'm going to stay away from that. The numerator, the lead coefficient's a 2. The denominator, the lead coefficient's a 1. So this limit is simply 2. Is that important? Yeah, that's bigger than 1. So although these terms were getting absurdly small, really, really, really fast, this diverges. And we always say by what test? So by the ratio test. Last day, remember, we had integral test, direct comparison test, limit comparison test. So how could that be? Because although the terms got really small really fast, you know, let's go out 1,000. 2 to the 1,000 is much, much bigger than 1,000 to the 10th power. 2 to the bazillionth is much bigger than a bazillion to the 10th power. Because the top I have an exponential function, the bottom I only have a polynomial. The exponential grows way faster. It just took a little while. In fact, how long did it take? Well, by the time, if I start putting large values of n in here, then n to the 10th over n plus 1 to the 10th is getting really, really, really close to 1. But then I'm multiplying it by 2. So after a little while, my numerators are looking twice as big as my denominators. Again, you don't see that right away, but that's what's happening. All right, so that one just seemed absolutely crazy. Now we're going to do the most challenging type. We're going to do one involving factorials that are being manipulated within the problem itself. So I'm going to walk you through, because algebraically, this next one gives people a lot of trouble. I'm going to have n factorial squared. On the bottom, I'm going to have 2n factorial. This is not trivial. This is not hard, but if I'm not really, really good with my bookkeeping right now, and I make even the smallest error, that will completely change the nature of the answer. So the tricky thing is when I replace n with n plus 1, what is it going to look like? When I replace n with n plus 1, this is going to become n plus 1 factorial squared. I am not squaring n plus 1. That square does not go on the n. No, 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 no. That'd be very, very different. I am squaring the factorial, so I need this set of parentheses. Now, how about here? Is it 2n plus 1? Yes or no?
No.
Why not?
The parentheses should be around the n plus 1, not the 2.
How about that? Is that correct?
Should be.
Therefore, my denominator is what? 2n plus 2. So I just showed you a place that people can easily make an error. I'm replacing n with n plus 1, which means it's 2 times the quantity n plus 1. That makes that a 2n plus 2. Sorry, I know it's a little hard to read. Let me put a little more space here. Again, replacing n with n plus 1. Now, I'll flip it over. Okay. It seems redundant that I'm putting absolute value in right now because I'm only dealing with positive quantities, but my quantities aren't always going to be positive. And next day, we're actually going to, or very soon, we're going to introduce variables into this mix. And so the absolute value actually is required. So I just want you to get used to it. Now, can I expand this? Yikes. This looks just nasty. Well, let's start with this. Isn't n plus 1 factorial equal to n plus 1 times n factorial? We know that is true. We also know that 2n plus 2 factorial equals 2n plus 2, 2n plus 1, 2n factorial. I'm whittling it down. I call it running off some terms. So if I said 12 factorial, that's 12 times 11 times 10 factorial. That's always true that you can do that. We showed that earlier. So when I do this guy and I do this guy, I'm going to replace them with these quantities here. If I can fit this in here. All right, so my numerator is going to be n plus 1 squared n factorial squared times 2n factorial. The denominator, if I can squeeze this in, 2n plus 2, 2n plus 1, 2n factorial, and then I have an n factorial squared. Okay, sorry about that, I was a little bit cramped. But now you see canceling all over the place. The n factorial squareds are going to cancel. The 2n quantity factorials are going to cancel. What does that leave me with? Well, if you really want to have some fun here, you could make that 2 times n plus 1, couldn't you? And if you did that, then what? Even one more term cancels. So after all of this, what am I left with? On top, you didn't have to do that step, but I think that step makes it even easier. Right now on top, all you have left is an n plus 1. On the bottom, you have a 2 times 2n plus 1. As n grows without bound, what is this limit? These are both first degree. The lead coefficient on top is a 1. The lead coefficient on bottom is a 4. So what is this limit?
1 over 4.
1 over 4. Here's the crazy thing. I have a factorial squared over another factorial. That's not geometric. That's not even like a geometric. Yet the funny thing is, as n gets bigger and bigger and bigger and bigger, this is acting like a geometric series with a ratio of 1/4. That sounds crazy, but that's what it is. An easy way to justify this, if you have a calculator and you took a large enough number, now the problem is you gotta be careful you don't go too big, but if I take a large enough number, let's say I went out 20, let's just say n is 20, and I put a 20 in here and I put a 20 in here and I calculate, I'm gonna get some crazy number. Now I put a 21 in there. And if I take the ratio of 21 over 20 as a decimal on my calculator, it's gonna look really close to 0.25. That's what I'm going to see. The ratio is getting closer to 1/4. Because that is less than 1, we say, therefore, and I'll just say the series converges by the ratio test. Crazy. The series converges by the ratio test. You can't look at this and just know it. And in fact, you'll look at things and go, oh, we did one just like that, but the next one might be the reciprocal of the one you already did. So then the results clearly will change. So the ratio test, if I see exponentials or I see factorials, it tells me the ratio test will be very good. Now, I do a ratio test, and I always do an absolute value. That way, if the ratio is negative, it doesn't make any difference. It's just I'm comparing it to 1. Is it smaller than 1 or not? What if we did a ratio test and we got a ratio of exactly 1? Here's the problem with that. We know that a geometric series with a ratio of 1 diverges. We know this. We know if the ratio is greater than 1 in absolute value, it diverges. If it's less than 1 in absolute value, it converges. And if it's exactly 1 in absolute value, it also diverges. But these aren't geometric series. They're acting like geometric series. They're asymptotic. So if one of these has a ratio of 1, we don't know if it converges or diverges, actually. That's not enough information. And in fact, here's a simple thing. If you do the ratio test and you get a ratio of 1, then you shouldn't have done the ratio test. It was the wrong test to do. The ratio test cannot yield a ratio of 1 if you were supposed to use the ratio test in the first place. If you get a ratio of 1, that means you should have done a limit comparison or the other ones. Oh, so the ones we did last day, you can't use ratio test on, and the ones we did today, you can't use limit comparison. They're completely separate. And I'm going to show you. Let's consider the harmonic series, because we already know that one diverges. And let's consider a simple P series, 1 over n squared, which we know that converges, we know that diverges. And I'm going to do the ratio test on both of these, because ratio test for a lot of folks is their favorite one. It's more algebraic. Limit comparison is still easier. I'm just taking one limit. Ratio test, I have to manipulate n plus first term, all that stuff, but it's more fun. So I'm going to do a ratio test on this one. So when I take the limit as n goes to infinity The n plus first term is this over the nth term. So this is n over n plus 1, and I know that limit is exactly 1. I just did the ratio test on the harmonic series, and the ratio test yields a ratio of 1. Okay? That means as I go further and further and further out, my terms are almost indistinguishable. 1 over a bazillion and 1 over a bazillion and 1 are so close together. Now let's do the ratio test on this guy. Same degree, Lie coefficient is a 1, and I get a 1. Yay! This one diverged, ratio test 1. This one converged, ratio test 1. That's all I need to do. I don't need to do another example. Anytime you are working with something that acts like a p-series, that's what we did last week. We mostly worked with p-series. Anything that acts like a p-series, that's a p-series, that's a p-series, you're going to get a ratio of 1. Because you shouldn't have used the ratio test. You should have used a limit comparison test and did a limit comparison versus another p-series. Okay, so if I have a rational function, I have a quotient of polynomials, and let's say the degree on top is less than the degree on the bottom, but the degree difference might be 1, 2, 3, 4, whatever. You're going to do a limit comparison test on that one, and you're going to compare to a p-series, and then you're going to get a really easy to understand solution. But if I take that same problem and I do a ratio test, doesn't matter what the question is, I will always get a ratio of 1. Always. So the ratio test cannot be used on something that a limit comparison should have been. Okay. So I said there were 2 tests today. Then there's another one, and it's called the Nth Root Test, or sometimes people just call it the root test. The nth root part's kind of redundant, but that's kind of the formal name. And again, going back to, I know that if I have something of the form and by the way, it doesn't matter if that's an n minus 1 and n plus 1, and you know, it's r to a power. I know this is geometric. I know it makes it converge. So let me throw a what if at you. What if I have a series of the following form? An to the nth power. And what if this an acts like r? What do you mean? How does an an act like an r? What if the limit as n goes to infinity of an is, oops, sorry. If I take a limit of that guy and I get a constant, I take a limit of that thing and I get a constant, and that constant is less than 1, then it means that this series acted like this series. It acted geometric. This is acting like an r. So it's acting like r to the n. If I have that situation, then it turns out I will converge. I will converge. It's kind of cool. Now, technically, this should be an absolute value, but this guy here is generally going to be positive. But if we want to still be strict, just in case it was negative inside. Let me do an example of this guy. Actually, I'd like to know the behavior of this series. Well, that n here makes it look exponential in nature, you know, like 2 to the n or 10 to the n, except that I've got n's inside. And well, I can try to do this one. I can try to do this one as a ratio test. Here's what the ratio test would look like. I take the limit as n goes to infinity of 3n plus 1 plus 4 over 4n plus 1 minus 2 raised to the n plus 1 over 3n plus 4 over 4n minus 2 to the n. If I flip that one up, I have different polynomials than these. Nothing's going to cancel. I can't combine them. I'm dead in the water. This is not going to work. This is a dead end. Okay. I can't use the ratio test on this one. It won't work. The stuff inside is still polynomial-ish. So, by the way, that scares me. But I have just written this as something to a power. So let's look at the something. All I have to do is consider the limit of that thing on the inside. And what is that limit? Anybody?
3/4.
It's 3/4, which is this one. This thing acts like, does this statement here make sense to you? This guy right here acts like this guy right here, because the limit of that term is 3/4. So this is a geometric series with an R of 3/4. This thing thinks it's a geometric series. It isn't, but it's asymptotic to 1, because as n gets bigger and bigger and bigger, this is getting closer and closer to 3/4. So this is acting like I'm going 3/4 times 3/4 times 3/4, on and on and on. So because this guy acts like this guy and this guy converges, that's all I had to do here. Therefore, I can say the series converges by the nth root test. You say, well, why are we calling it the nth root? Because technically, what is this right here? It's the nth root of that right there. So if I can write this as something to the n, then I'm only looking at the inside. I'm looking at the guts of the term. Okay. Now, the nth root test is not going to be one you're going to use a lot, but when it's appropriate, it's usually really, really simple. It's usually really, really fast. Okay. So I'm going to prove something to you first. I'm going to prove a very important statement mathematically that's going to come up a lot when you use the root test. Okay. Okay, what if I had something of the form n to the 1 over n power? That's not one you see a lot of. If I had something, 2 to the 1/2 power, that'd be the square root of 2, cube root of 3, 4th root of 4, 5th root of 5. That's not one that you probably run into. I want to prove this, and I'm going to prove something else so that you never have to prove it again, so that you can use this result forevermore. So if I do this as e to the log of n to the 1 over n, you know what happens. That comes in front. This becomes e to the 1 over n log n. Isn't that just log n over n? I brought the 1 over n in front. So last step is e raised to the limit. And we've done this before, of log n over n. This is an indeterminate form of, this is the infinity form, but it is a perfect candidate for L'Hopital's rule. This is, by the way, the main reason we use L'Hopital's rule, believe it or not, is not for the limits we did before, but the limits that are going to come up, stuff like this. So this is now e to the limit as n goes to infinity of what? Of 1 over n over 1. And as n goes to infinity, this term approaches 0. So this is e to the 0 or 1. This limit is 1. Now I'm going to go one step further because the next one is going to be just as valuable and it will save you some time. Same question. K over n for any positive integer k. So in other words, not 1 over n, but it might be 2 over n or 3 over n or 10 over n or 50 over n. K is a positive integer. Okay. So actually what I should do there is let me, clearly I need K is a different color. So in this case, that's a K. You're going to like this one. So now that's K, because it's K over N. So that's K. So that's K. And as N goes to infinity, isn't this still approaching 0? It's still 1. So here's a very, very powerful limit. This limit, you can forever do 1, and you don't have to rederive it every time it comes up. I mean, every time it comes up. Every time you use the root test, you're likely to get that limit, believe it or not. It's going to come up a lot. So let's do a really simple example, and I want to show you something. The ratio and the root tests are ridiculously similar, and often you actually have a choice. If it's factorial, ratio test and nothing else. But if it's exponential in nature, ratio or root test every time. You can actually use the root test on an exponential. So let's consider the following. Let's say, I'll keep it simple. I've got n cubed over 3 to the n power. Okay, and let's start by using the ratio test. So if I use the ratio test, my first step is take the limit as n goes to infinity of n plus 1 cubed over 3 to the n plus 1. That's the n plus first term over the nth term. So I'm going to go times 3 to the n over n cubed. Okay. Well, I get a lot of canceling with the 3's. And so my denominator is going to be 3n cubed. My numerator is going to be n plus 1 cubed. Can I evaluate that limit right now without doing anything else? Can anybody see it? If I do no other work, can I just give you the answer? If you can, give me the answer. What is that limit?
1 over 3.
1 over 3. Because the degrees are the same. The lead coefficient here is a 1. Here it's a 3. That's just 1/3. Piece of cake. That means that this series is acting like 1/3 to the n. So that n cubed on top, n cubed is growing without bound, but 3 to the n is growing so much faster, it's not even close. Okay. See, if I replace n with a large value, n cubed, yeah, that might be big, but 3 to the n dwarfs it. It's the n cubed. What if I replace n with a million? Million cubed is huge. But 3 to the millionth power makes that look microscopic. Yeah, these are acting like a geometric series with an R of 1/3. So we'll say, therefore, the series converges by the ratio test. That's what we just did. Now, I want to do the exact same problem, but now I want to use the root test. That means I need to rewrite the problem. How? I need to rewrite it so that it looks like this. Remember, to use the root test, it has to be a quantity raised to the nth power. There's no exception to that. Quantity to the nth power. Okay, I'll handle the denominator. Okay, good. You guys cool with that? All right. How do I do the numerator? Anybody want to try? How do I?
Is it n to the 3 over n?
N to the 3 over n. Oh, well, let's see. What's the rule of exponents? I multiply them. So that's 3 over n, that's third power, and that's, okay, yeah, you're right. This quantity is exactly equal to this quantity. Why did I do that? I have to do that because the root test, that's the thing I'm going to take the limit of. So the next thing we're going to write is, what's the limit as n goes to infinity of n to the 3 over n over 3? Well, the first thing I'm going to do is get the 3 out of there. So let's first write that as 1/3 because I don't want that to get in the way. That 3 on the bottom is just enough to confuse me as to, how do I do this overall limit? It's a constant. Get it out of there. All right, now I have n to the 3 over n. Didn't we just address this? I just proved that n to the k over n, that limit is always what?
1.
1. So what's my answer? 1/3 times 1 or 1/3. So this, oh, sorry. And that's less than 1. Wait a minute. It's feeling very deja vu, isn't it? I did the ratio test. I got the ratio. The ratio means I got that consecutive terms have a ratio that is approaching 1/3. So it's acting like a geometric series of 1/3. That's the ratio test. I'm looking at consecutive terms. The root test was, no, I looked at it as I just flat out wrote it like a geometric series. I wrote it as something to the nth power, and then I proved that guy is acting like the number 1/3. So the routes that I took were very different, but both conclusions were exactly the same. Both the ratio and the root test are because you believe the original series acts like a geometric series. Technically, it's asymptotic to a geometric series. And in both cases, we came up with the ratio of 1/3. Well, no, we probably should have come up with the same ratio. We were using the same series, two different means, same series. So we'd say, therefore, this series converges by the nth root test. Whenever you have something that's exponential in nature, n cubed is not exponential. 3 to the n is exponential. If it's exponential in nature, you can always use a ratio test, and most people will. But you can also always use a root test on that one. And the actual limit taking might be less work with a root test, okay? But you could have gone either way, and they both were correct. That's the only time you have the crossover between ratio and root tests. If, again, factorial involved, can only be ratio tests. And the nice thing about factorials with the ratio test is everything's always going to cancel. You're never going to end up taking the limit of a factorial because all the factorial terms will always cancel every time. Okay? This is a crazy one. Now, I'm going to show you the coolest one of all. My own personal favorite. What if I got something that looks like this? Can I use a root test on this one? See, I see that end to the end. I'm thinking root test. Can I use a root test on this one? Based on what I've just said. Anyone?
Got a good feeling, yeah.
Can I use a root test?
N factorial to the 1 over
factorial?
n?
I have an n factorial. What's the only test I can possibly use? The only test.
Ratio test?
Ratio test, yeah. Factorials, ratio test, that's it. If you've got a factorial, there is no other test. Ratio test, period. Now the top looks, God, it looks like I could use a root test, but I can't on the factorial, so I got to use a ratio, which makes the top really icky. Because remember a little while ago when I did the rational function to the nth power, and then you replaced the n's with the n plus ones, and I said you can't use it won't work. Well, it turns out in this case, I don't have a choice. This is just nasty. I don't want to say pure evil. This one's actually probably my favorite of all the limits to take. Yeah, it is. Okay, it's a little evil, but you know, we sometimes like to dabble in, you know, sometimes it's fun to be bad. You know how that works. All right. So I want to take the limit of consecutive terms. So that would be n plus 1 to the n plus 1 over n plus 1 factorial. Yikes. Now, as much as I would like to cancel, I can cancel here, but I cannot cancel here. Why can't I cancel? Different bases, different exponents. So, I mean, what's going to cancel? Well, let's see. Let's get as far as we can. So let me rewrite a couple of the terms. How about if I rewrite this one as n plus 1 times n factorial? And how about if I write this one as n plus 1 times n plus 1 to the nth. Now stare at that for a moment and convince yourself that that is true. Say, why would I do such a crazy thing? Because now I could at least cancel that stuff. So what am I left with now? Now I'm left with n plus 1 to the nth on top. And on the bottom, I'm left with n to the nth. Well, at least they have the same exponent. Well, numerator and denominator both approach infinity. I could try using L'Hopital's rule, except that it would be an infinite number of steps and I'd never actually get an answer because n is also growing. So so L'Hopital's won't work. Now, here's what makes me laugh, because some people say, well, now I learned this is just going to be 1 because, and then I'll get all the reasons why. No, the answer's not going to be 1. No, and you can't use degree as the argument because this n isn't a constant. Degree only works if that's a constant. But could I do this? Is this true?
Yep.
Now, that term is definitely approaching 1. So does that mean that this is just 1 to the infinitieth power? No, not even close. Isn't this one of our indeterminate forms? Isn't that one of the ones we just did in the previous chapter? Yeah. And by the way, the answer isn't 1. You can't say, well, no, I'll take the limit. By the way, this is what I'm seeing a lot of people do. They're saying, and this is equal to the limit as n goes to infinity of 1 to the nth power, and then that's 1. They're taking the limit of part of it, but not all of it. And some of you, I've made that comment on your quizzes saying, you can't take the limit of part of it. You got to take it all or none. If I take the limit of the inside only, then the answer would be 1, and that would be the wrong answer because you can't do limits that way, ever. And if you got the right answer doing it that way, that was an accident. It doesn't work in general. In fact, it doesn't work a lot more often than it does work. This is the right type of indeterminate form, and I can do the e to the log, or I can just be really, really lazy. Well, can I pull those apart? If I pull those apart, what do I get?
One plus 1 over n.
Huh. You know, I got the strange feeling I've seen this before. Hint, hint, hint. I think I've identified this as the single most important limit in the history of the world. And I'm not joking. It's the single most important limit there is. What is this one? We've done this more than once in this class.
E?
E. Oh my gosh, after all that, the limit is E. But I never would have seen it here. I wouldn't have seen it here, but by breaking it up. By the way, could I have done the e to the log thing at this point? And then, yeah, I would, and I would have eventually got e, but it would have taken me a lot more steps. Breaking it apart was a lot easier. Whoa. Now, go back to here. Oh, by the way, greater than 1? Yeah. So therefore, this diverges by the ratio test. Now you know why this is my favorite one, because it's just so much fun. And it turns out this is the one we're going to use the most often. Let me pull out, I had it a moment ago. Hold on. Let me grab my schedule. Sorry. Here it is. That's all a mess in my office area. Okay, so today is lecture number 14. We have one more lecture that will be on the next exam, and that's the last of the tests. And we're not actually going to learn a new specific test. We're going to look at a particular type of problem that incorporates all of the tests that we've learned up till now. And so the last new material is going to be the day we get back. So it looks like there are 8 lectures on this test. You had 7 lectures on the first test. There are 8 lectures on this test, and we've already gone now through 7 of them. So 7 of the 8 topics you've got. I believe I've already posted the practice test in the key. So William says he's going to study all the break, but hopefully not all the break, but it might be a good idea before we come back on Monday for you to have taken a look at the practice test, because again, 7 of the 8 lectures are already on there. Clearly there'll be a couple of questions that you won't recognize. And you'll go, oh, that's probably new material. That's usually the way it works. You'll know because you'll see series with -1 to the n. Those are called alternating series, where they change sign every term. That's what we're going to do next. Because I said first of all, there's no such thing as a restriction on a series in terms of the signs. And again, of all the series you ever deal with, they're usually going to alternate in sign. So that's not even an issue. That's the last stuff. And then the exam itself is, I think, 3 weeks from today. Now that's kind of nice. We have one more lecture, but the exam's not for 21 days. So I don't need you to be preparing for 21 consecutive days, but at some point in those 21 days, yes, you probably want to do a little bit of review and some work on that. So that's where we are. I will go ahead and stop here.